Yes, do you have any questions? Any curiosities? Oh yeah, we had that problem, right? Can you remind me the problem number? Yes, okay. So this was basically the question. We had some potential barrier. U was equal to U0 if x is between 0 and L and 0 otherwise. So this is how the potential looked like. This is L, this is U0. And we are sending a particle from here. It's a charged particle. We also know that due to the radiation back reaction, the acceleration of a particle is given by some time scale times the derivative of the acceleration plus the force over the mass. And in this case, the force, you see, the force is nothing but the gradient of the potential. So there is no force acting on the particle unless x is equal to 0 or x is equal to L. And the force, we can write it as plus 1 over m minus u0 Dirac delta x. This is the force at x is equal to 0 plus u0 Dirac delta x minus L. Basically, we need to solve this differential equation to see how this particle will behave in such a potential. And we are considering the case that the total energy is less than U0. This is one thing that we will be interested in. So classically speaking, there shouldn't be, the particle shouldn't be able to go from x less than 0 to x larger than 0. It's not allowed to go there. But here, there is you see, there is the potential energy which due to energy conservation it cannot go through, but there's also this additional force, this radiation back reaction, which might change the behavior of the particle. And that is what we are trying to solve. Now, I will make several assumptions. First of all, I will assume that the acceleration is continuous so that I can talk about its derivative. Sorry, the acceleration. Okay, so let's see. I have to satisfy this equation all the time. I know that there are certain Dirac deltas over here, which this derivative might include some Dirac deltas in it. But if the derivative contains Dirac deltas in it, then the acceleration should be, this can be discontinuous. So I have discontinuous acceleration, but finite. Since the acceleration is finite, the velocity will be continuous. It will change continuously. Since the velocity is continuous and finite, the position will change continuously, etc. So we can solve, I mean, whenever you have these Dirac deltas in whatever question you have, what you do is you just try to avoid the Dirac deltas as much as possible. And one way to avoid it is to solve your equation for x less than 0, x larger than 0, but less than L, and x larger than L. So we will solve in these three regions, the differential equation basically takes this form. A is equal to tau A dot. Because as long as x is not equal to 0 or x is not equal to L, all the Dirac deltas are 0. What is the solution of this equation? A of t will be just e to the power minus t over tau times a at t equal to 0. Well, on the left-hand side, the particle is moving with constant velocity. That is our initial condition. Let's say at t is equal to 0, my particle is at the point 0. At t is equal to t1, my particle is at the point L, if it ever reaches that point. So for t less than 0, A of t is equal to 0. It moves with constant velocity. Then it reaches this barrier. In this barrier, there will be forces, and hence there will be acceleration. So this is let me label those regions. This is region 1. This is region 2. This is region 3. At the time t less than 0, it is in region 1, and the acceleration in region 1 is always 0. Now, for t between 0 and t1, the acceleration will be a of, again, t is equal to 0, its power minus t over tau might be now, the acceleration need not be continuous, as I said. It can have some jump. So let me see how much the accelerating changes as I go from x less than 0 to x larger than 0. So let's look at the discontinuity of the acceleration. Well, this is my differential equation. Now, of course, there is this complication that here the derivative is with respect to time. I would rather have a derivative with respect to the position. But I can just change that. A dot is equal to dA by dx times dx by dt. This is dA by dx times the velocity of my particle. And as I said, velocity should also be continuous because acceleration will be finite. So my equation for x is this one, dA by dx is equal to, well, dA by dx times v times tau is equal to a minus 1 over m minus u0 Dirac delta of x plus u0 Dirac delta of x minus L. Or dA by dx is equal to a over v times tau minus 1 over m v times tau minus u0 Dirac delta of x plus Dirac delta plus u Dirac delta of x minus L times u0. Now I can integrate this over dx from x0 minus to x0 plus. Well, on the left-hand side, I would get a at x is equal to 0 plus minus the acceleration at x is equal to 0 minus should be equal to, well, let's say I'm integrating something over an interval of 0 length. In general, it will be 0 unless that thing is infinite. So it's just like the integral will be basically the value of my function times the length of the interval. If the length of the interval is 0, unless my function is infinite, that product will be 0. Well, here if you look at this term, v is finite. In fact, it is whatever the initial speed I send it to. tau is finite, A is finite. So the integral of this one just gives me 0 over this interval. The only thing that might contribute is this one, thanks to the Dirac delta. The Dirac delta diverges at x is equal to 0, and hence this term is the term that will contribute, and that difference is just u0 over mvt. This is u0 over m, let me call it v0 tau. This is how the acceleration changes as I go from x is equal to 0 minus to x is equal to 0 plus. So basically, since it doesn't accelerate before hitting the barrier, the acceleration, now I can say t is equal to 0 plus, just as it's crossed the boundary, should be equal to u0 over m v0 tau. v0 is the initial speed with which I am sending my particle. Now, this tells me that you see, this is the general form of the acceleration in every region. Well, I have determined what the acceleration is at t is equal to 0 in region 2. So that tells me that the acceleration in region 2 as a function of time should be equal to u0 over m v0 of tau e to power minus t over tau. This is my acceleration in region 2. Again, v0 is a constant, is the constant velocity with which I send my particle, the initial velocity.
Minus u0 is?
Well, let's see. Here there is a minus, here there is a minus, it makes a plus, so this is plus. You see, basically this tells me that if my particle kind of enters region 2, and it seems that it is possible to enter region 2 where classical is not allowed, it will keep on accelerating for a time that is determined by tau. Of course, the acceleration will die off. The acceleration in region 2 is still positive. It is moving faster now. Now let's continue. In region 3. Well, basically I repeat the same thing.
Hocam bir şey sorabilir miyim?
Yes.
Şimdi potansiyel sabit olduğu için mi bir kere accelerate ediyor, sonra yavaş acceleration azalıyor?
Let me just copy this first and I will answer your question. Well, you see, what does the radiation back reaction tells us? It tells us that if the particle is accelerating, it will be emitting radiation, and hence due to this emitted radiation, it will be losing energy. Okay. So that is why the acceleration, you see, here in this problem, we don't have any force. The particle shouldn't be accelerating, in fact, except on its own acceleration. Since there is no external force causing my particle to accelerate, this back reaction force gets smaller and smaller. But there is an external force when at x is equal to 0. That causes the initial acceleration. That causes the start of the radiation back reaction. And then there is no external force to cause my particle to accelerate. And then it keeps on decelerating. Hold on 1 minute. Did I make a mistake over here? Yes, this is not minus, this is plus. This is the solution we have. Kind of due to this radiation back reaction, it keeps on accelerating. And hence this is plus. This is plus. Again, it's due to this radiation back reaction, which, well, the acceleration seems to be increasing. Now we will, now what happened? The particle is coming with constant velocity. It hits my barrier. That starts this radiation back reaction. Then it keeps accelerating in this range. And then eventually it will come to the other end of my barrier. Now, at the other end of my barrier, I know what the solution is on the other side. The A3, let's say, the acceleration in the third, when my particle enters the third region as a function of time, let me write it in this form, A at T1 times e to the power T minus T1 over tau. This is the acceleration in the third region. Now, I know what the acceleration in the second region is. This is the acceleration in the second region as a function of time. Now I need to find I know that the acceleration will change discontinuously across the second boundary. Now I have to find what that discontinuity is to be able to determine this initial value A of T1. Now I will do basically the same thing, but this time not integrate over 0 minus to 0 plus, but I will integrate from L minus to L plus. So integral of dx from L minus to L plus, just from the left of that boundary to the right of that boundary. And again, this term just gives me, the first term in the integral will tell me what A acceleration at the right of the boundary is, minus the acceleration at the left of the boundary. The first term will again be 0, because I'm integrating over an interval of 0 length. I only receive contribution from the second term, and that is from the second Dirac delta, not the first one. And I would get minus u0 over m, let me call it v1 of tau. Now v1 is the speed of my velocity of my particle when it hits the second boundary. That is also something I have to evaluate. So the acceleration at, well, let me give this a label 3, at T1 plus, right after it hits the second edge, minus the acceleration before it hits the second edge, that difference should be minus u0 over mv1 times tau. Or the acceleration in the third region at the time T1 should be equal to the acceleration in the second region at the time T1 plus u0 over minus u0 over mv1 tau. Now the acceleration in the second region is given by this expression over here. So that is equal to u0 over mv1 of tau times e to the power minus or plus t1 over tau. This is the acceleration in the second region at the time t1. Now this is v0 minus u0 over mv1 of tau. This is the acceleration in the third region at the time t1. So that allows me to determine what the acceleration in the third region is as a function of time. This will be equal to u0 over m tau, 1 over v0, e to the power tau 1 over tau minus 1 over v1, times e to the power t minus t1 over tau. This is the acceleration in the third region. Now, I still need to find what v1 is. I didn't yet determine v1. And to determine v1, let's go back to the acceleration in region 2. So this is nothing but dV by dt in region 2. So if you just integrate this, velocity in region 2 as a function of time t is just u0 over mv0 times e to the power t over tau plus some constant t, c. This is the velocity in region 2. v1, okay, so I have some initial conditions. The velocity should be continuous. So the velocity in region 2 at the time t is equal to 0, this is right after it crosses the first boundary, should be equal to the velocity in region 1 at the time t is equal to 0. This is just before it crosses the boundary. But the velocity before it encounters the first boundary, we had defined it to be v0. So the velocity in region 2 at t is equal to 0, which is u0 over mv0 plus c should be equal to v0, or c should be equal to u0 over mv0 minus v0. This is our c. So as a function of time, the velocity as a function of time t is equal to u0 over mv0 e to the power t over tau plus u0 over mv0. So here this is minus, this is plus, sorry. Minus plus v0. Or this is equal to u0 over mv0 e to the power t over tau minus 1 multiplied by e to the power t over tau, no, sorry, u0 over mv0 e to the power t over tau minus 1 plus v0. Now v1 of t, well, we had defined this as u0 over mv0 e to the power t1 over tau minus 1 plus v0. This is this is not v1 of t, this v1. This is just v1, which is defined as the velocity in region 2 when t is equal to t1. Now let's go back. What is the velocity in region 3? Now acceleration in region 3. Was this one. This is equal to u0 over m. Well, just substitute what v1 is. I'm not going to do that. And well, let's see what we have. Now, the velocity in region 2. Well, if you want some sensible solution, let's say, what you would like to have is that the acceleration in region 3 should be 0. That's what you would like to have. I mean, you have a particle that's moving at constant velocity, something happens in a given region, and then it leaves that region where there is no force, and even there is no back reaction, let's say, then there is no acceleration. So you would rather have zero acceleration in third region. Well, this will tell us that V1 should be equal to V0 times e to the power minus T1 over tau. Well, V1 we had already calculated. U0 over mV0 e to the power T1 over tau minus 1 plus V0 should be equal to V0 e to the power minus T1 over tau. Well, we still need to find what T1 is, at least what it satisfies. So this is V of t. L, that's the width of the barrier, is the integral of V2 of t over time from 0 to T1. This will be equal to U0 over mV0 tau times e to the power T1 over tau minus 1 minus T1 plus V0 times T1. This is the equation that gives T1 in terms of L. And then, well, if you want to evaluate whatever you want to evaluate, you can just go ahead and evaluate it. Of course, if the particle is to reach T, if there is such, you have to be able to find a T1 that is larger than 0, for which this is larger than 0 also. For example, if you look at, I don't know, if you look at V2, as t increases, does it increase or decrease V2? As t gets larger, it increases, so it's always positive. So my particle is moving forward through the barrier. And let's see. And V1 will be larger than V0, it is accelerating. 1 over V1 will be smaller than 1 over V0. Right? 1 over V1 is smaller than 1 over V0, so that the acceleration in the third region is always positive. It will never be 0. At least we solved it. It seems to be possible to go through the barrier, but still we have the problem with the radiation back reaction. It just doesn't make too much sense.
Hocam peki bu yüksüz parçacık olsaydı?
Then there's no radiation back reaction.
O zaman parçacık bariyeri geçmez.
No. You see, the main issue over here is the existence of this term, the A dot term. You see, it's this term that makes the whole difference. if that term was not there, the acceleration should be continuous all the time. It can diverge, and in fact it does diverge. There is an infinite force, but there is an infinite force, so it cannot just keep going. It just bounces back.
Yani kuvvet sadece x eşittir sıfırda bir etki ediyor, bir de x eşittir y.
If it reaches those points. That's the external force, not the radiation back reaction. Radiation back reaction exerts whenever the acceleration is changing.
Aslında parçacık birinci rejimde de acceleration yaparak gidiyor.
You see, what we are assuming here, our initial condition was that the particle is coming with a constant velocity in the first region. So there's no acceleration over there. Since there is no acceleration over there, there is no radiation back reaction. So it's moving with constant velocity. But then it hits the first boundary. So it's accelerating at that boundary. But if it is accelerating at that boundary, it means there will be radiation back reaction. And since the acceleration goes from 0 to non-zero value, the force of radiation back reaction is also infinite. The external force is infinite, the radiation back reaction also turns out to be infinite. And hence, although there is this infinite force due to the barrier, it seems as if the particle can just go through. Now, I would say this is a pathological example, not really a nice one. It just demonstrates some tricks that we use to solve some differential equations with Dirac delta functions, mainly. Now, the question that it was kind of addressing is, in quantum mechanics, somehow there is this tunneling phenomenon, which we also observe. I mean, your electronic devices are working because of this tunneling phenomenon. But in electronic devices, at least, our observations are for systems that are charged. So maybe it is this radiation back reaction that forces the particles to go through regions which classically they wouldn't be allowed without this radiation back reaction. But I think that it creates more problems than it solves. So without really understanding what this radiation back reaction is or how to deal with it, I mean, such an answer would be more problematic, I would say. Other questions? Other curiosities? Not necessarily about electromagnetism.
Şimdi bizim elektrik field, magnetic field falan yazıyor. Ondan sonra işte gravitational field. Hep bir field'dan bahsediyor. Field ne işe yarıyor?
Well, you see, what we call a field is basically some function that has some value at every point in space. So we can talk about functions whose values are numbers. Well, those we call multivariable functions in mathematics. Or you can call them scalar fields. Or you can have functions whose values are vectors. At every point it gives you a vector. That is what we call mathematically a vector field. So what is an electric field? Well, it's basically a function that at this point there's a vector, at this point there's a vector, at this point there's some other vector. So at every point in space and time, it tells us what is the direction of the force per unit charge, which is a vector. So that's why we call it the vector field. For example, in fluids, you would like to know the velocity of the object of the fluid at every point. That will be a velocity field. I mean, calling a function a field is basically just some way of calling, well, it's just, wherever you say a field, you can just call it a function. And instead of electric field, you can prefer to call it the electric function. Magnetic field, magnetic function. Velocity field, velocity function. It's not really something fancy. It's just a different way of calling a function. But that's, I mean, we are trying to describe what is happening at every point in space and time. So we are assigning certain quantities at every point in space and time. And those since we are assigning certain quantities at everywhere in space and time, that is how we define what a field is. That's the meaning of the word field, dictionary meaning.
I have heard that, actually, I'm not sure if it's correct or not. I've heard that if we apply three fields, I mean gravitational field, electric field, and magnetic field at the same time to a mass, it can travel in time or something like that. Is it
No.
correct, or is it just...
Well, you see, now Earth is like exerting a gravitational field on you. There's the gravitational force. There is well, there are some charges everywhere around. There's some electric field in your position, small one. Also gravitational and magnetic forces. Do you travel in time? No. Well, there are all these speculations or conspiracy theories about I mean, I think they all started with some military experiment in the, I think, mid-1900s, where they claimed that the ship was in a strong magnetic field and it just disappeared. And then it just reappeared after a given time, and the people in the ship were not aware that they had disappeared, and all their clocks were behind by the amount that they had disappeared. So they are saying, oh, they traveled in time. Of course, there's no, this is a classified document, and somehow all the people are aware of these hidden, secret documents. But still, it's secret. Nothing. It never disappeared, probably. There's no scientific documentation. Other questions? Well, people always fantasize about magnetic fields, what they can do. There are all kinds of perpetual motion machines which create energy from nothing using magnets. And of course, they don't exist.
Şimdi her şey büyük patlamayla başlayabiliyor ya işte. Büyük patlamadan önce mesela zaman var mı?
No. Well, it depends on your theory. I mean, for most of the theories, there was no time. Well, time started with the Big Bang. Even the term before the Big Bang doesn't exist, the concept of before the Big Bang. Because if you want to talk about before and after, you have to have the concept of time. If time starts with the Big Bang, there is no before. We don't know. There are many speculations about that also. One of them, especially the string theorist, says that, okay, the space-time is in fact 10 plus 1 dimensional, not 3 plus 1, and we are just living on a brain. And then they say that there are many brains in this extra dimensions, and at some time, they just collided, two brains. And hence we have all this creation of particles. Well, in this scenario, there is time before the Big Bang. So these brains are just moving in these extra dimensions, and they just happen to collide at a given time, which we call the t equal to 0, or the Big Bang time. This is one possible theory. And an alternative is that, okay, this is not the first Big Bang, but the space-time just explodes, expands. After some time, it starts collapsing, and it collapses in a big crunch, and then it bounces back. It's just like you drop a ball, and it just bounces up and down. So some say that that might be what's happening to the universe. We don't know. Well, there's nothing much we can do to test it. That's the problem. So we are just looking for consistent theories that are both mathematically consistent among themselves, internally mathematically consistent, and consistent with our current observation. There are some other theories which say that, okay, before the Big Bang, there's no before the Big Bang, but if you just use the terminology vaguely, there was no time. It was all 4 space dimensions. And there has been a phase transition for some reason, after which one of the coordinates was transformed into the time coordinate. And some say that we are living in a black hole. And probably the time t is equal to 0 was when the black hole was formed. Why should it come from outside? It might be already inside. If there's something outside. You see, when the black hole forms, already it has a huge amount of mass.
Her şeyin önemli başlangıç noktası olmalı.
Which theory says that it should? So it doesn't have to be. But does everything have an initial point? Well, the universe seems to have started from a very compact object. That's what observation is telling us. We know that they are moving, all of them seem to be moving away from us, so if you just play the tape backwards, they should be approaching us. So everything should be in a very small region. We don't really know what happens before that. But if you assume that everything just continues the way it is now, everything should start from a point, which is what we call the Big Bang. But that's kind of a huge hypothesis. When everything was very dense, I mean, they can behave completely in different ways. We don't know how they behave at those times. Okay, so let's end the lecture. Let's end the semester also. Cuma günü yapmayalım. Sınav zaten pazartesi. Değil mi? Salı. Çarşamba mı? Hey. Ben buralardayım. Sorunuz olursa beklerim. Geçen hafta Deniz Bilimleri Enstitüsü'ne gittim. Bizim öyle bir enstitümüz var, biliyor musunuz? Evet, deniz var ya Antep'te. O yüzden oraya kurmuşlar zamanında.
Böyle bir yer var da hatırlıyorum da.
Deniz Bilimleri Enstitüsü Erdemli'de.
İşte o Erdemli'den.
Mersin'de. Akdeniz sahili.